Welcome to the campus of North Idaho College and today's broadcast of the North Idaho College Public Forum. The crew is comprised of Welcome to the campus of North Idaho College and today's broadcast of the North Idaho College Public Forum. The crew is comprised of North Idaho College television students. Your moderator is North Idaho College political scientist, Tony Stewart.
Today we start a 3-week series with the Department of Geology at Eastern Washington University. In this 3-week period, we wish to discuss geology and particularly stress volcanoes after the eruption at Mount St. Helens and also the minerals of our area. On program number 1, our topic is Geological Characteristics of the Pacific Northwest. We wish to welcome to our program from the Department of Geology at Eastern Washington University, Professor James Snook, who will discuss geologic mapping in northeastern Washington. Also, Professor Eugene Keever, catastrophic ice age floods in the Pacific Northwest will be his topic, and Professor Buzz Walker dealing with scanning electron microscope applications to geology. Gentlemen, welcome to our program. I'm happy to also have on our program the panel for the questioning of our guests. First of all is Richard Snyder, and second is Janelle Berg. We will invite Janelle Berg to commence the questioning.
Beginning with Professor Snook, oftentimes we drive on the highway and we marvel at the beauty of the rocks around us, and we also wonder at what we're seeing. Can you tell us what some of the typical formations are in the eastern Washington area?
Well, in the Spokane area, we're blessed with having a wide variety of geologic features available. This is one of the reasons that we have an active department at Eastern. There are 3 major rock types: igneous rocks, sedimentary rocks, and metamorphic rocks. They're all represented in this area, in the immediate vicinity. In fact, Spokane is situated in part on volcanic rocks, flow rocks. If we could see the first slide, we can see the kind of phenomenon that produced much of the land surface that we see in eastern Washington. The outpouring of great quantities of flood basalts along cracks and fissures in the Earth's crust provided numerous lava flows, as you see in the slide, filling up what was potentially, eventually, a basin. Here's one of the lava flows that we can see in the sides of Grand Coulee. Spokane itself is situated right on the edge of this basalt filling. Immediately to the north are metamorphic rocks and igneous deep-seated rocks that have been intensely deformed, as you can see in these slides. Further to the east and further to the west, we have some economic deposits that are found in sedimentary rocks. The Red Marble Quarry in the last slide is an old magnesite quarry. Here we're looking at the Okanagan Valley, which shows the nature of some of the igneous metamorphic base. And then the sedimentary rocks in the same general vicinity, showing stratified, layered sedimentary rocks. This is the base upon which our whole area is sitting at the moment.
Richard Snyder.
Professor Keever, it's my understanding that the Pacific Northwest, particularly northern Idaho, northeastern Washington, has had a very rich geological history. And as an archaeologist, of course, I'm very interested in things like the last glaciation that perhaps came down into northern Idaho and northern Washington, the Lake Missoula event that was associated with that. And as a kind of personal interest, I'd love to know if you think all of those glacial advances are gone forever, or are we really living between 2 glacial advances?
Yeah, I would say that our area is very rich in terms of the most recent geologic events to affect even including the May 18th event, but even before then, we've had a series of very interesting geologic events, such as the glaciation that, of course, affected all areas of the world in terms of climatic change. But at this particular latitude, we're far enough north to feel the direct effects of the glaciers. And so glaciers did indeed, as recently as probably 12,000 years ago, there were still glaciers in northern Idaho and in Washington state. So glaciers affected all of our valleys to the north of us. Probably are not known whether they reached the Spokane area, but came fairly close in some of the valley systems. And of course, associated with this, as you inferred, the Lake Missoula event that created a very large lake that resulted in some very catastrophic flooding coming through the Spokane area and the eastern Washington area. If we could maybe look at the first slide, might be able to see better on a map. This shows the eastern Washington area, and it shows the area that was inundated by some of these catastrophic floods. Glaciers blockaded the drainage up around Pend Oreille Lake, created a very large lake, a lake that contained some 500 cubic miles of water. And when the glacier melted, or occasionally when that water broke loose, it essentially flooded the entire eastern Washington area, creating the channeled scabland area that's very unique in all of really in the world. Nowhere else has a flood of this magnitude really been verified by geological means. We might look at some of the other slides. This shows a little bit better perhaps the ponding or the damming of the Clark Fork River where it enters the Lake Pend Oreille area, creating that very large lake which was held in by a dam, an ice dam some 2,000 feet thick. Very precarious, and it did let go a number of times, sending surges of water through the eastern Washington area, scouring and changing the landscape very profoundly. This is an example of some of the kinds of deposits to the south of us associated with some of that catastrophic flooding. As you can see, very large boulders tumbled around, deposited very, very rapidly. Very interesting kinds of deposits that can be seen in many gravel pits in the eastern Washington area, including the Spokane Valley. Many of the deep gravel pits that are in the valley are in these kinds of flood sediments. Here we can see the effects of the floodwaters running through the Grand Coulee area over the famous Dry Falls area that was created partially by the diversion of the Columbia River by ice and also by the floodwaters scouring through the Grand Coulee region, forming a huge waterfall that migrated upstream and was essentially shut down as the floodwaters expended themselves. Then the water supply was cut off. Some other very interesting things in the eastern Washington area and even in the Spokane Valley. The particular slide you see here is from an area around Odessa, Washington. We're looking at giant current marks, giant current ripples generated by currents of water that were very difficult for us to imagine unless one imagines something like the Teton Dam, for example, bursting. And even that wouldn't be of the magnitude of the kinds of floods that we had experienced here in the eastern Washington area. I think the next slide shows an air view. I think you can see very nicely again the little corrugations on the topography there. Those again are some giant ripple marks. We have a number of these in the Spokane Valley. There's some near Newman Lake. There's some up by the golf course just to the north of us over here. A number of other areas show the same types of features. So we do know that there's been a tremendous amount of water coming through here as recently as some 13,000 years ago. Not all the sediments are that large and coarse and spectacular. Some are much finer, and this is actually a cut through one of these giant ripple marks in around the Edwall, Washington area. And it's fairly interesting because there's some light-colored layers in there. And although I think maybe most of us could probably guess what those layers are, that is Mount St. Helens ash, approximately 13,000 years old. So this was not, May 18th was not the first time that we've experienced that kind of activity. And your third question, well, I should point out this is Liberty Lake, and the flood currents that came from the left-hand side moved down the Spokane Valley, deposited a ridge of sediment directly in front of the valleys that enter into the Spokane Valley. And so if one visits Liberty Lake, you're looking at a pendant bar. It's a flood deposit. You'll see the same sort of thing at Newman Lake, Spirit Lake, and some of the other lakes in around the Rathdrum Prairie and Spokane Valley areas. And your third question, whether we're through with the ice ages, depending which geologist you talk to, probably most, I think, would say that we are probably not out of the ice ages. There has not been enough time since the retreat of the last glaciers to say that we're really over the hump. It's only been a mere 10 or 11,000 years. To a geologist, that's not really long enough to say for sure that we're out of ice ages. We've had longer episodes of very warm climates in the last 2 million years, and yet we have returned to glacial-type climates.
Could I follow up just a second? A short one. If I understand you correctly, you're saying that around Spokane, the South Hill and the North Hill are approximations of the original ground level, and that everything that's below that, downtown Spokane, the river, the whole thing, that's part of a wash that was cleaned out by this breaking of an ice dam from Lake Missoula.
Yes, everything in the Spokane Valley was under actually a considerable amount of water. In fact, we even had glacial lakes standing in the Spokane Valley. The ice that dammed the area around Grand Coulee backed water all the way up into the Spokane area, and then put on top of that another 300 or 400 foot deep flood surge running through here means that most of the Spokane Valley was indeed inundated during these flood episodes.
We've talked with Professor Snook a little bit about the rock formations in the area, and we've talked a little bit about the history of geology in the area. Let's go back to Professor Snook again and ask some questions about what can we expect in the future. Are there faults in the Spokane area, and what are those faults apt to produce?
Well, yes, there are lots of faults in the general area. Most faults, however, are of such a nature that they're not extremely accurate right at the moment. Some of the lakes to the south of us have rather recent faults, but by recent in geologic terms, we're talking about tens of thousands of years. And so immediate concern is not that great. We lie in an earthquake area which is not the most active. It's not the least active either. It's somewhere in between.
In terms of, you mentioned lava earlier. Where did this lava come from? What kind of production?
Well, liquid rock is generated either within the crust or below the crust of the earth. And since it is lighter than, liquid is lighter than the solid, it simply rises along weaknesses in the Earth's crust. And in the case of the basalts that we have to the south of us, covering most of eastern Washington, eastern Oregon, southwestern Idaho, this particular type of fissure eruption coming along cracks is rather unique. There are two other basins in the world where we see this same situation, but we don't have these things erupting right now. Usually volcanic activity, extrusive activity, is restricted to some sort of generation of a cone. We don't have that with the kind of source that we have for the basalts that we have to the south.
One more just very short question. When you drive west on the freeway from Spokane, you see the outcroppings in the freeway, or near the freeway, in the center divider of the freeway. What kinds of outcroppings are those, and how can one tell what kinds of characteristics to look for?
Well, as you go up the hill to the south, you're in the basalts from the Columbia River Basalt group. These are the fissure eruptions. What you're seeing are some of the cooling features that you get in these lavas. As they come out in thicknesses averaging about 65 feet, roughly, but varying from a matter of a few feet to several hundred feet at the time they came out, these things cool then over a long period of time. It takes a long time for the heat to be transferred to the atmosphere, and as a result, contraction features develop. And the columns that you see up near the intersection of Highway 2 and the road that goes out to the airport produces almost perfect 5- and 6-sided columns. This is a part of that cooling pattern. You see this just in certain portions of these lava flows, near the bottom and near the very top.
For those people who have tuned into our program in progress, I would like to inform you that this is the first of a 3-week series with the Department of Geology at Eastern Washington University, and we're talking about such things as geological characteristics of our area, and later we'll talk about volcanoes and minerals of the Northwest. Professor Buzz Walker is also with us and among our 3 guests. And Professor Walker, I believe that you're using something called scanning electron microscope applications to geology. I know in all fields we're using modern technology to do a better job than in the past. And I believe you have one of these new machines at Eastern Washington University. What does it look like? What does it do? And what effect is it going to have on geological studies in the future?
Okay. The scanning electron microscope was developed about 15 to 20 years ago for commercial uses. And we've been talking about the macro world of geology, and I'd like to talk a little bit about the micro world. If we could see the first slide, this is a picture of a scanning electron microscope at Eastern. The microscope is owned jointly between the Department of Biology and the Department of Geology. The microscope itself consists of an electron column, which you could see on the left, and this has an electron gun and electromagnetic lenses and scanning coils, which direct an electron beam onto a specimen. Well, then we have a detection system that detects secondary electrons generated in the specimen, and then this is displayed in the cathode ray tube, just like a TV screen you could see there on the right-hand side of the picture. Well, the scanning electron microscope has the capabilities of magnifying objects about 100,000 times, whereas a regular light microscope can conventionally magnify about 1,000 times maximum. And it also has great resolving power, where it could resolve particles, 2 particles, as close together as about 100 microns, which is approximately 1/10,000th or less of an inch. And so it has extremely good resolving power. Well, what we use the electron microscope for in geology is we look at microfossils, we look at the, say, oil reservoir rocks to determine their properties and how we could best evaluate that reservoir to extract oil or natural gas from it. We look at minerals and we look at different ores and try to determine how to extract, what methods of beneficiation that we could use. Looking at on a very micro scale, we might be able to see where gold particles are. And we might then say, well, we need to crush the rock to such and such a size in order to get the gold out of the rock. So that's just a few examples. I've shown here some slides. This is a reservoir rock with sandstone being cemented by the mineral aragonite. And so what engineers may be able to do is go in and acidify the reservoir rock and therefore produce more porosity and permeability and recover more oil. Here's just a close-up now showing that same rock. We have next. Okay, this is a specimen in which gold occurs, and just the finely divided, these are, the magnification here is approximately 500,000 times. And the gold occurs in the little joints in between the columns there, and they know just how they have to go in and crush that ore. So this is a series of minerals which are found in evaporites, deposits evaporating from seawater. And here we could see what types by the various crystal morphology that we deal with.
Concerning your study, have you found, with this new equipment that you have, any information that is of great significance that you did not know before for our area in particular? I'm thinking of such things as our discussion before the program. We talked about possible oil deposits, and we were talking about shale, which is in certain parts of the West, and so forth. What have you come up with?
Well, we're right now evaluating some of the coals in Washington with the scanning electron microscope. And what we're trying to do is determine the ancient environments in which these coals were deposited by looking at the spores and pollen within the coal, which would not be observable under standard microscopy methods. So once we could determine the precise environments, and we have to keep in mind the coals in Washington range in age from about 50 million years to about 15 million years old, and so therefore are very young coals. So if we could determine the specific environments, we could then compare it with modern-day analogs of these environments, and we could work out the geometry of perhaps of the coal basins simply by using these microfossils and the types of plants and spores and pollens that exist in these coals.
As we will learn in program number 3 concerning some of the minerals, silver and gold and so forth in North Idaho, you are saying, or am I reading into it, that we may have some other economic advantages here concerning something we have not thought about in the past? In other words, is there a production of coal possible in the future in this area?
Yes, there is. Presently in the Grand Ronde region of the state, which is there at the corner of Idaho, Oregon, and Washington, interbedded with the basalts that we talked about previously, are lignite coal beds up to, they think, 40 feet thick. And presently there's been industrial interest, and they have been drilling for these coals and trying to determine if it would be economically feasible to go in and mine these coals out. So yes, and in fact the state of Washington right now has the 7th largest coal mine in the nation, which is located over in the western portion of the state at Centralia, Washington.
Richard Snyder.
I'm dying to know, what does Mount St. Helens ash look like under your electron microscope?
The St. Helens ash has essentially 2 different features to it. It has what we call a glassy feature, which is a very irregular shaped particles, and very irregular shaped. And the other feature, which is less common in the ash, is the mineral or crystalline substances, and these appear as primarily lash-shaped to rhombic-shaped particles. It's quite interesting, the ash itself, and you could see why it's so abrasive, the ash, to automobile engines and to your throat and what have you, just because of the angularity of the material itself.
In other words, it's very, very coarse, it's quite an abrasive, and you would predict coming into contact with it will cause damage.
Well, no, I wouldn't predict that. I would hesitate to say that, but I'm sure if you breathed enough of it that it would be deleterious to one's health. But as far as carcinogenic aspects of it, I wouldn't have any idea. Most materials that are carcinogenic are fibrous in nature, and really the glass isn't. It's more equine in nature. So I would hesitate to say as to the health aspects of it.
If you can see Mount St. Helens ash exploded 100,000 times, I would think you could become so familiar with it that you could spot that ash wherever it came from and say, this belongs to Mount St. Helens, not Mazama or Baker or somebody else. Can that be true?
Some people claim that they can observe the characteristics of the ash and make those statements. I would be hesitant to fingerprint ashes may be better on a chemical basis than a morphological basis.
Before the program, we talked a little bit about writing and knowing what we were looking at. And I wonder if Professor Keever could tell us some books, first of all, that might be helpful as you ride about in your car or traveling, that would help us to know what we were looking at. And secondly, where some of the places are that you could go to look at some of the evidences of the ice floods in the Northwest.
Okay, I think probably for the people in Spokane and northern Idaho as well, there is a little pamphlet available from the U.S. Geological Survey on the channeled scablands of eastern Washington, and that can be obtained down at the Federal Building here in Spokane. It's a very reasonably priced, I think 75 cents, and it gives a very quick summary of what some of the geology is over here. Beyond that, there are some other books, one entitled Regional Geomorphology of the United States by William Thornberry. That would be an excellent reference book for one to read up on this particular region. There's one called Roadside Geology of the Northern Rockies by a couple professors at the University of Montana at Missoula, Professor Alt and Hindman. That would be an excellent book for one to look at as well. And of course, areas to go. It's everywhere. Any of those valleys that come down from the north, the Colville Valley, the Priest River, the Pend Oreille, all of those valleys have contained glaciers, have very spectacular scenery, and have some very good evidence of the effects of glaciers there.
I must interrupt. I'm sorry that we're out of time. I want to first of all express appreciation of our staff to the three professors from Eastern Washington University for your most informative comments today. Ladies and gentlemen, I hope you've enjoyed our program and that you'll be with us again next week and the following week when we'll be continuing our discussion with the Department of Geology at Eastern Washington University. Next week we're going to stress volcanoes as the major topic, and particularly Mount St. Helens, and then also refer to what might happen at Mounts Rainier and Baker. I would also like to express my appreciation to the staff at KSPS Channel 7 and Bill Stanley in particular for allowing us to tape these programs in the studio, and to express our appreciation to his student crew today from North Central, Lewis and Clark, and Rogers High School. I hope all of you will be with us again next week at the same time when we will continue these discussions with the Eastern Washington University Department of Geology. Until that time, have a good week. I am Tony Stewart.